Kia ora, my name is Yohan. I'm a Year 13 student from Wellington College, and I would like to introduce you to my project, Smashing Headaches, which is a spectroscopic analysis into the decomposition of paracetamol. And I'll let you work out the play on words for yourself. Paracetamol, which was first made in Europe in the 1850s, is now the most commonly used over-the-counter drug around the world. It is commonly taken to relieve mild pain and fever, including headaches. Paracetamol works by blocking chemical signals to our brains, and it also regulates body temperature, which assists while fighting fevers. Paracetamol is most commonly taken in a tablet form, which contains 500 milligrams. It is also the most misused drug in the Western world, and accounts for the most drug overdoses in the United States, United Kingdom, and here in New Zealand. So, I wanted to find out if the drug decomposes over time, and if so, what the decomposition products are. If paracetamol does decompose, it could explain the reason for a number of overdoses, as people would be taking more than the recommended amount to have any pain relief. It also speaks to the relevance of storage conditions of the drug, whether they're just precautions or they should really be followed. The paracetamol molecule contains a few functional groups: the amide, the aromatic, carbonyl, and the hydroxyl. I hypothesize that the paracetamol will decompose in two ways, through a hydrolysis reaction or an oxidation reaction. In the hydrolysis reaction, the water molecule, which is a nucleophile, will attack the amide bond, creating paraminophenol and ethanoic acid. A hydrolysis reaction essentially splits the molecule at its weakest link, which is the peptide or the amide bond. Or, if oxidation occurs, NAPK will be produced. This molecule is responsible for overloading the liver, which in extreme cases can cause it to shut down. People with weak livers especially, from drugs and alcohol, find it hard to detoxify this product. I also believe that decomposition will follow the exponential decay pattern. I have designed my experiment so that I analyze samples left in certain conditions over a certain period of time. Every 2 days, I put a new crushed sample on my windowsill, which was exposed to air, heat, and moisture. I decided to crush the tablets to increase the rate of reaction by increasing the surface area, as I did not have the luxury of time. As there aren't many public studies on the decomposition of paracetamol in non-lab conditions, I decided that it was more important to show if there was at all decomposition, rather than being true to the time period itself. This can always be done in a future study. I also put sealed vials in an incubator at school, set to a constant 75 degrees Celsius, and the final sample environment was directly under a UV torch with a wavelength of 395 nanometers for the time of 7 hours. I then used a method that I wrote with the help of Dr. Courtney Davey from Victoria University to extract the paracetamol from the samples and determine the mass of said paracetamol. NMR, nuclear magnetic resonance, was then carried out on a few of the samples and pure lab samples to determine the reliability of my method. I came up with the idea for this project in late April. As soon as Term 2 started, I began researching ways to extract the paracetamol from a tablet without HPLC equipment. I found a simple method from the Royal Society of Chemistry and built on that. I then contacted Dr. Courtney Davey from Victoria University, who agreed to assist me and supervise me while conducting these experiments in their undergraduate labs. I ran pure paracetamol samples from the labs through a UV Vis spectrophotometer, which I used to calculate the molar absorbance coefficient in Beer-Lambert's law, which is a formula that explains the relationship between concentration and absorptivity. Then I attempted to synthesize my own para-aminophenol to compare the decomposition products in the filter cake too. But this was ultimately a failure, but thankfully we did find some para-aminophenol in the university storage. I extracted the samples left for the longest amount of time in each condition. However, due to the weighing for the cuvette, some of these samples were inaccurate. I then carried out the weighing and analysis of more samples from my different environments. And then NMR, or nuclear magnetic resonance, was then used to determine the reliability and accuracy of my method. I then finally contacted Douglas Pharmaceuticals, which confirmed my hypothesis of what paracetamol would react to become. This simple method was found in a publication by the Royal Society of Chemistry. The tablet has non-active ingredients such as starch and flour, which I wanted to separate the paracetamol from. Paracetamol will dissolve in the acetone, and the binders and fillers which are insoluble can be filtered out. The filtrate is to be left in a fume cupboard overnight for the acetone to evaporate, leaving in theory colorless paracetamol crystals behind. This method had a few key issues though. Firstly, the crystals were a pink hue instead of white. Because this sample was left overnight, it is highly likely that it reacted with oxygen in the air, creating NAPK, which is a highly conjugated molecule, thus is likely colored, unlike most organic crystalline solids. Also, out of the 500 milligrams in a standard tablet, I was only able to extract 270 milligrams, which is only about a 54% yield. Through observation, I noticed that acetone evaporated quite rapidly when I spilled some on the desk. It was gone in seconds. And the drips from the filter paper started steady and then slowed down. This is the filtrate coming through. This could mean that the acetone in the acetone paracetamol solution was evaporating while trying to get through the filter cake in the filter paper, leaving behind paracetamol in the filter cake. There was nothing that I could do about the filtration, as the school did not have a Buchner funnel. However, I could prevent oxidation and reduce the evaporation time by using distillation. This is more or less a closed system, but to be safe, I decided not to use a Bunsen burner to heat it, as acetone vapor is highly flammable. I opted for a hot plate and a water bath. This method was very consistent. However, the yield was still quite low, and as you can see, the paracetamol crystal yield from distillation did not have a pink hue. This would support the idea that the pink coloration was due to oxidation. It was after those improvements that I went to speak with Dr. Davey. I outlined that the issue was in filtration, and that I'd require a UV Vis spectrophotometer as well. She was kind enough to supervise me in the undergraduate labs and teach me how to use some of the specialized equipment such as a Buchner funnel and rotary evaporator. The Buchner funnel uses an aspirator to create a partial vacuum, which sucks the filtrate out, leaving behind a dry filter cake. This method left a negligible mass of paracetamol in the filter cake. I'll talk about this towards the end. The filtrate was then poured into a round bottom flask, which was attached to a rotary evaporator, which lowered the pressure inside the flask and created a vacuum. This lower pressure lowered the boiling point of methanol, which allowed it to evaporate at low temperatures. The mass of paracetamol was recorded, and a sample of the crystals was taken out using a spatula to create a 0.033 gram per liter solution for the cuvette, which then went to the spectrophotometer. I then used this data to back calculate using Beer's law the mass of paracetamol in said sample. Before I put my samples into the UV Vis spectrophotometer, the machine was calibrated with a blank sample of the solvent, methanol. And then I put in a cuvette containing this concentration of paracetamol, pure from the lab. I exposed that to a spectrum and found that its max absorbance, or lambda max, was at 248 nanometers, which was quite close to what I read on the internet. I used the absorbance data at 248 nanometers to back calculate the molar absorbance coefficient. This is Beer-Lambert's law rearranged to find epsilon, the absorbance coefficient, which is equal to the absorbance value at lambda max over the width of the cuvette multiplied by the concentration. The units are a bit different for this calculation, where the length or the width of the cuvette is actually in centimeters instead of meters. Before we dive into calculations, here are some of the controls for my experiment. Firstly, I assumed that each paracetamol tablet from the Panadol brand contained exactly 500 milligrams of the active ingredient. I decided to use Panadol because they are the most reputable supplier of the drug in Australia and New Zealand, and also the most bought brand by Kiwis. I put many controls in place through my procedure to ensure a consistent and reliable method. You can read more about these in my final report. Here are just a few of the things that I did keep constant when analyzing each sample. This is how I back calculated the mass. I found the concentration using the absorbance value and Beer's law. I then found the number of moles in the cuvette, and using that I found the moles total of the paracetamol, and then I found the mass of the paracetamol. The three equations that I did use are here at the top. So I randomly selected 4 windowsill samples to analyze. That is the left column. It tells you how many days exposed they were. The middle column is the mass of the crystals after evaporation, so left in the round bottom flask, which could contain moisture and impurities. The right column contains the mass of the paracetamol after back calculating using Beer's law. You can see that the mass of paracetamol and the mass of the crystals follow a similar trend, which you can see that there is a clear correlation between mass and time. The trend appears to be exponential decay. However, it is hard to be certain because there are few samples there. There are not enough samples to draw finite conclusions. Just note that my example for 14 days exposed is inaccurate. I've included it on this graph because it is raw data, but due to a weighing issue, that data is unreliable. When paracetamol was left in ultraviolet conditions for 7 hours, only 343 milligrams out of the 500 remained. And also when paracetamol was left in an incubator set at 75 degrees Celsius for 1.5 hours, only 277 milligrams out of the 500 milligrams remained. Although it was ultimately a failure, I did want to share how we did plan on synthesizing 4-aminophenol. So initially we thought that the lab didn't have any para-aminophenol on hand. Hence we decided to synthesize our own using a paper by Dixon and Patel, which is referenced in my final paper, in an effort to determine the decomposition products in the filter cake. Essentially, 250 milligrams of pure paracetamol was dissolved in a 4 molar solution of hydrochloric acid and reflux for 30 minutes. It appeared that the paracetamol fully dissolved. 25 mils of dichloromethane was added to the 4 molar solution to dissolve any paracetamol that didn't react with the HCl. This created a chlorinated organic layer, which is in fact heavier than the aqueous layer, and thus would be the shaded liquid on the diagram to the left. The aqueous layer on top contained what we believe to be the protonated para-aminophenol because it was produced in acidic conditions, and a salt. This layer, of course, was highly acidic. The filter funnel was tipped upside down so that all the paracetamol left in the aqueous layer was exposed to the DCM and dissolved. The organic layer was disposed of and the aqueous layer was kept. The 4 molar solution was diluted into a 2 molar solution and then split into 2 equal aliquots of 25 mils. The aliquots of 10 mils and then 5 mils, a 2 molar NaOH solution was added until the aqueous solution was neutralized. This, in theory, would have deprotonated any para-aminophenol, which was the desired product. However, upon further analysis through NMR, we discovered that we were left, in fact, with paracetamol, which would suggest that either the right solvent was not used or that the reflux was not carried out for long enough. I used nuclear magnetic resonance, or NMR, to validate my method and try to highlight the decomposition products. Atomic nuclei with odd mass numbers have a magnetic property called spin. This makes them observable using NMR. Proton NMR focuses on the hydrogen nuclei, which is essentially a proton, and has a mass number of 1. The hydrogen nucleus has a magnetic moment, and when placed into an external magnetic field, it can line up with the field or against it. It takes less energy for the nuclei to align with the magnetic field and more energy to line up against it. The nuclei can only align one of two ways, and these are called its spin states, and each one has a clear energy difference. At the right frequency, radio waves can be absorbed by the nuclei and it can flip states. This is called resonance. A detector in the NMR machine can measure the frequency and intensity of the waves which are absorbed. This data is then plotted on a spectrum. From this NMR spectra here, and I've gone into way more detail in my research paper, you can see that what we believe to be synthesized paraminophenol is actually pure paracetamol, as the peaks on the spectra line up. In these spectra, we've compared pure paracetamol and the extracted paracetamol crystal. As you can see, there are very little impurities. We definitely have extracted paracetamol from the tablet, and the difference in mass of the crystals and the pure paracetamol are likely to be different due to moisture retained in those crystals while they were formed, rather than impurities, as we can see in this NMR spectra. These two spectras compare the extracted paracetamol crystal and the filter cake. As we can see that in the filter cake there are trace amounts of paracetamol, but if you look closely at the scale of the spectra, you can see that these are minuscule amounts of paracetamol being found in the filter cake. And because of all the controls I have in my method, this would be consistent, hence the results are comparable and are reliable. These two spectra compare pure paraminophenol, which Douglas Pharmaceuticals did state to be the most prominent decomposition product, and the filter cake. However, we cannot see any pure paraminophenol in the filter cake, which would suggest that the conditions were not right for paraminophenol to be produced as a decomposition product. So I wanted to talk about why this project is relevant. Obviously, the conditions I had, 75 degrees in an incubator, might seem extreme, but actually, according to drivingtest.co.nz, within 10 minutes in 24-degree weather, the inside of a car can reach 38 degrees. And within half an hour, it can be 50 degrees. Imagine what would happen if you left your paracetamol tablets in a car outside in hot weather for days on end. There are also the issue of old people pre-popping pills and storing them incorrectly in damp conditions or non-airtight containers near windowsills or heaters, which could potentially be detrimental to their health. The crushed tablets might have not seemed relevant, even though I did not have the time to use full tablets. The crushed paracetamol is relevant because factories store Panadol in a powdered form before it's molded into tablets. So essentially from this project, I can confirm that paracetamol does decompose over time. There is definitely a correlation between mass remaining in time. However, the decomposition products are inconclusive, and further research or a future study would have to be done to determine that data. So this project really only scraped the surface. There is definitely far more detail that this project could go into. So some suggestions for further work is not crushing the tablets and exposing those tablets to different conditions for a period of for months on end. Now that we know that there is a correlation between mass and time, it's definitely worth doing much longer experiments. I also think it would be valuable to leave multiple samples for each duration and each condition to find an average, which would make results more reliable as well. Testing different brands and different types of paracetamol would be great to draw more broader conclusions. And also, I thought it would be cool to test the polymer packaging used to protect the tablets, to see how well does it absorb UV light, distribute heat, and protect the tablet from moisture. I also think more NMR should be done on the samples, to ensure that each sample is reliable and that the data is reliable. However, this will require a much larger budget. My project did not have a budget, so I was quite lucky to use NMR at all. So here are my sources. There are a few more sources in my final report. I am still in the process of converting my sources into a recognized system such as the Harvard or the Oxford system. And finally, I'd like to acknowledge the Wellington College Science Department, my chemistry teacher, Mr. Bruce, and of course, Dr. Courtney Davey and Dr. Joanne Harvey from Victoria University, who supervised me and guided me through the equipment, through some of the experiments at their undergraduate labs. Thank you for listening, and I look forward to hearing your comments on my experiment. Cheers.